Welcome, everybody, to this great webinar. My name is Aaron DeYonker. I run the products team at eMeter, a Siemens business, and I'm very happy today to bring to you a couple of my distinguished colleagues. First off on the list is Chris King. Chris is our Chief Regulatory Officer within the Smart Grid division at Siemens, a role that he played at eMeter for many years before taking on that broader role globally. He's been very instrumental in many regulatory events and legislation areas, consulting on technology issues with Congress, with public utility commissions, across the globe, and he was instrumental in the eMeter strategy and product alignment here. I also want to introduce Lars Johnson, Chief Technology Officer for the Smart Grid Group. Lars was one of the founders of eMeter and has been in this space for many years like Chris, and both of them have a wealth of knowledge to share with us today on distribution optimization as it comes to AMI. And without further ado, I would like to turn the floor over to Lars.
Thanks, Aaron. Good morning. We've been working on this smart grid and smart metering problem now for a few years, and I guess just as a refresher, many of the problems that we're trying to address with the technologies that we collectively call smart grid, are really aimed at solving some of the key problems that we face as an energy industry right now. And everything from incorporating, new forms of renewable energy, reducing peak demands in order to, improve asset utilization, reducing system losses as well as non-technical loss in the overall delivery of energy. And certainly after some of the recent events, which seem to be becoming more numerous, outage prevention, restoration, and more resiliency in the network in order to improve power service and reliability to customers, and all the while trying to continue to drive operating costs and become more efficient in operations. Really leveraging technology. So some of the things that we could claim as tools here, have many new sources of data, but sort of at the center of data sources right now, and certainly something that's referenced all the time, is the massive amount of new information that's being generated by smart meters. And we sort of see the smart meter as a focal point here, partly because that's really where we've been working, but also because it represents the demarcation between the customer and the supplier. And so in this sense, the supply and delivery of energy to consumers really is, for the first time with smart meters, sort of bringing the customer into the overall energy equation. And as such, it becomes a center, but it's not the sole new data source. It is a focal point right now, but what it's going to lead to is the ability to have more and more information about both sides of the grid. That is, more instrumentation out into the distribution network, especially the low and medium voltage network that's not particularly well instrumented today, but also more information about what's going on with the customer, both new sources of energy that they may be running themselves, microgrids for small campuses, smart appliances, solar metering, and so forth, and then new loads and new sources such as energy storage and electric vehicles and so forth. And then, of course, we have to couple that with all of the other information that is available from utility systems today, and basically say, how are we going to make use of this, and in particular, how do we take this beyond, let's say, the initial deployment of meters in the meter to cash sense. So some of the things that we look at here, and I think maybe. Wrong slide there. But I think what we're seeing here is that this, for the first time, is the instrumentation of the grid. So if you look at the simplified view of a network here, and you consider that you have basically meters at every particular endpoint. What's important here is that this metering information is being collected not only more frequently with higher resolution, but it's also time synchronous. That is, that instead of having meter reads that are once a month that are being scattered across the bill cycle, so that you're really only getting, 5% of your meter is read each day in a manual metering. I'm sorry, each month in a manual metering system. You are essentially getting time synchronous information at, say, 15-minute resolution or hourly resolution for every meter, and with that information, you're actually able to do some very interesting things that you haven't been able to do before because you've had no real data that was timely or time synchronous. So, aligning 15-minute intervals across multiple different points allow you to do things like aggregate that data and come up with a load curve that says, hey, all those customers on a feeder, on a 15-minute by 15-minute basis every day represent the following load, something that you haven't been able to do without putting some kind of special metering device out on the feeder. And that's a new capability that's quite important. We'll talk some more about that. In addition to that, we're able to take a look at what happens when we see different outage events, and to be able to look at not only where they are in the grid and understanding what the pattern of outages is, and this is in a nearly real-time sense, but we're also able to understand better what the restoration activity is. So we can see real-time events coming from meters at the restoration level. And being able to aggregate this information, again, by circuit level makes for some interesting analysis. Momentary events are also a very important problem, and you'll hear some more from Chris on the value of some of the power quality statistics and improvements there that we can generate by having this better information. But being able to look at momentary events down at the circuit level allows us to consider that, okay, we may have problems at a particular location that is are being triggered because we have power quality problems that could be related, for example, to tree trimming and intermittent operations because of recloser operations and so forth that up to now maybe haven't been observable from the from any other systems within the utility operations domain. So being able to have that information in real time and be able to respond to that is obviously an important factor in improving outage performance and power quality. As we look at this time synchronous information that is being collected at all of these points, this idea that we can create virtual devices or virtual metering points where we can say, look, if we summarize all of the loads, aggregate all the data at these endpoints, we can actually summarize loads up into the grid and create virtual load points up at different higher levels. And what that allows us to do is actually pretty profound. If you think about how things are being done today, we don't really have that kind of information. But now, with that information, we can say, we're able to actually create a load on a particular device, such as a low-voltage transformer. And we're able to look at that information and analyze that in the context not only of what the rated capacity is, but also look at it in terms of how long that device has been at or above a threshold for an aging and a potential failure standpoint, correlate that with temperature, and basically provide information and insights into where we have the potential for problems. So there's many areas today that people are concerned about in terms of distribution operations, and one of them is injection of new renewable energy, solar loading, and so forth. Another is electric vehicles. And if you imagine that we have this information from smart metering, we certainly can say, where are we today in terms of our load capacity on each of these individual devices? And then let's monitor that and make sure it's not going to get to a problem where we have to worry about a failure, and if necessary, go out and proactively change things. So in some circuits, there's potential for some technical or non-technical loss that exceeds what you look at as your threshold. And what we're seeing in some markets is the the implementation of metering at different levels of the grid that is non-revenue. So we're not talking about a meter-to-cash problem here. We're talking about installing meters for telemetry purposes. And one of the big applications there, in some parts of the world they call it energy balance. In other places they call it non-technical loss. But we're basically saying, are we getting paid for all the energy we deliver into the circuit? And to do that appropriately, to analyze that appropriately, it's often nice to have another sensor that tells us, okay, this is what's being injected at the head end of that circuit, and then compare that to either the real or virtual meter points that are indicating power consumption downstream. So yet another way to look at how this information can be used. So just looking at some of the different ideas of why are we doing this, I think most of this we can say we're really coming back to how do we, as a company, as a utility, improve our fundamental services to our customers. And I think it's important to have notional aspects of service level agreements or KPIs. And again, you'll hear Chris talk a little bit more about how some of those KPIs are being used now to drive business value. But these are really in the area of service availability, service quality, and then I think a new one here is sort of a capacity, the ability to deliver service both now and in the future. And in each of these areas, we have different applications that involve, how do we actually achieve those KPIs? So in the area of availability, we're really talking about outage and restoration and being able to use information to improve metrics in both of those areas, as well as to provide preventative and proactive measures to avoid outages. In the area of service quality, this is often back to the combination of sort of the hard outages, but also voltage, power factor, other kinds of actual quality of service metrics related to the actual delivered energy, which in this case would be volt var management and sags and swells and so forth. And then from a capacity standpoint, this is really probably, in part a planning model, but it also has to do with some real-time applications. But looking at how do you plan for the model, how do you plan for the service delivery in a distribution grid, make sure that you have enough, and then also how do you look at being able to optimize that capacity where you may have targeted demand response programs and so forth. So just, all of this can lead to, assessing yourself and saying, where are we today with those metrics? Where do we want to be? And then how do we target investment in the grid or in technology in order to help us optimize? And in this area of constrained budgets, it's not like you can necessarily go out and do, wholesale replacement of circuits or transformers or go out and put smart grid devices everywhere you might like to. So I think there's an obvious need to say let's figure out how we target that. So this is certainly an approach to using data to help you to drive some of those targets here. And some of the areas, of course, in transformer sizing, tree trimming, targeted deployment of distribution management system capabilities or volt var management or DSCADA type applications, and then looking at where you really do have either reconductoring or sectionalizing opportunities to say I can further optimize my investments. So a lot of different areas for improvements. Again, optimizing based on some of the specific data that is available, and smart metering data being a first point of use here that we can start to put some of this information into creating some of those goals. And then, of course, tracking goals. I mean, in typical process control fashion, you may want to set your goals and have some monitoring level in terms of saying, okay, if I exceed certain thresholds, I've got a problem. I've got to go do something differently. But then also having some ways to say, that I'm not satisfied with just tracking to a fixed goal, but I want to actually show that over time, I'm going to be making investments in change methodologies to. In order to provide improvement and to track and trend my progress in that sense. Looking at that, I mean, what do you need? How do you get there? And I think the field of meter data analytics is certainly one way to get started. I think we've seen that baseline your performance. That is to say, you can say how am I doing on those metrics today, whether it's outage, energy loss, asset loading, and so forth, and basically say this is where we are today. And then use that information to drive your view of what's your priorities. Where do you want to make more investments? Where are the investments going to be most valuable? Sort of support that business case for the investment and ROI. And then as you start to implement each of the programs that may have different components to them, again, whether it's technology or asset investment, to use the analytic capabilities based on meter data, but not just revenue meter data, but also other sensors and grid-specific devices. But basically, to monitor those programs against your targets and to make sure that you're making progress. So certainly a key thing here is the creating a foundation, and we believe that a smart grid application platform that successfully integrates data from a number of different types of field devices, certainly AMI meters being one category of device, but other devices, whether they be grid sensors or customer-connected loads, it's an important platform of information for those aspects that we just mentioned. And then, looking at how that platform is, tightly integrated with many of the different business processes that you have within the utility. That this represents the ability to not only take advantage of the data itself from an analytics perspective and give you that sort of roadmap to improvements, but also a platform for applying further technology and automation to actually take some of the actions that we've mentioned here and automate some of those processes. So with that, I will pause and turn it over to Mr. King.
Hey, Lars, this is Aaron. Before we do that, we have a couple questions here for you. One of them is, how much faster can utilities detect outages with AMI as opposed to the way they've been historically doing it? How does AMI help with that turnaround time?
We've had various people report their findings on this, and I think you can look at the data coming in real time from smart meters as potentially cutting something anywhere from 15 to 30 minutes off of your outage detection time. It's been pretty profound, actually. So I think it's the first part is very important. You're getting this before most customers have had a chance to call in or decided to call in.
The other one here is the system diagrams you showed. The value seems pretty clear, but there's a lot of integration complexity that could happen with that sort of implementation. Is there sort of a way that AMI helps from an architecture perspective to streamline some of those interfaces between all the systems within the utility?
Well, so I think this is an important architectural question, and what we've tried to do is to say we can really provide a common point of access to all of the utility business systems and operational systems for that AMI data, so that AMI data is readily available in a form that's easy to use by those different systems. So in that sense, we tend to look at the smart grid application platform as a unifying environment for access to the business value and the operational value of AMI and smart field devices in sort of the last mile of the distribution grid. And that certainly is an important part of making that integration challenge easier. But with a disparate, legacy of different systems and different age systems and so forth, the integration challenge is certainly important. But that's, again, part of what we're trying to address with the smart grid application platforms. Do that job once and then be able to use the data and the applications for many different purposes.
Great. So a common point of governance and integration for all the AMI-facing stuff so that it's uniformly accessed by all the other systems at the utility.
Exactly. And every time you put on, you want to add some new capability or put some new application to work, you don't have to go and redo all those interfaces.
Great. Okay, I just wanted to remind everybody that you're free to ask questions through the tool here, and we will get back to more of those at the end of the presentation. And at this point, I will turn it over to Chris King.
Thank you, Aaron. So now I'm going to turn to the regulatory side, and the main question I want to answer here is, why do we care about any of this? And there are a couple of reasons. One is that there's a huge economic potential for society in this. And then the second is that in working with their regulators and having the right incentives, utilities can benefit significantly on the financial end as well. And as you'll see, as I go through this, we're talking about tens of billions of dollars, so some real money here, as they say in Congress. So I'm going to talk about some specific savings opportunities. What's reliability worth? How much is it worth to reduce the number of outages or shorten them? And then I'm going to dive into a case study with ComEd, Commonwealth Edison, which is the utility in Chicago, Illinois. And they have a very comprehensive program built around using AMI data for operations. Now moving on to reliability savings, there are about 6 different specific ways in which outages are either found faster or repaired more quickly, identified more accurately, more efficient dispatch of personnel. Marsh mentioned some of the momentaries analysis, so that allows for better deployment of capital. One thing, utilities are going to spend about $100 billion a year on investing in their systems. That includes all of their areas, and distribution's about a fourth of that. So very significant number. If you can spend it even 10% more wisely, you're much better off. And then we have seen some published examples of savings around outage prevention and restoration. EPB, which is the utility board in Chattanooga, Tennessee, in the big July 2012 storm last year, found a savings of $1.4 million. And they are a medium-sized utility with several hundred thousand customers. So that would scale depending on the size of the utility. If you had several million, of course, it would be much larger, and vice versa for a smaller utility. In Hurricane Isabel a couple of years ago, Pico Energy found that they saved about $500,000 in just that one event. So these things obviously don't occur all the time, but there are typically, a couple of bad events a year. In fact, we just had some big storms in the last couple of weeks in the eastern part of the country. They also found that that was on a single event, and then on an ongoing basis, they report nearly $500,000 a year in savings. Going on to the next area, operating the grid itself, looking at line losses is the first area, and this comes from a little bit of it is theft. A surprising amount is equipment issues. Another area of losses that can be improved is for feeder lines that are unbalanced. So if you are overloading a feeder, a circuit, then the losses are going to increase. So if you lower the overloaded one and put some of the load on the other one, you'll reduce your losses. When we look at this, about for a typical U.S. utility, losses are around 7%. And 7% is not a big number, but on the other hand, it's worth about $24 billion a year for the industry at retail rates. How much can that be improved? A lot of that is, in fact, most of it is technical losses that cannot be eliminated. It's going through the transmission lines, and a big part of that is actually going through transformers, either in substations or even the pole-top transformers. So you can do a tiny bit there through improved equipment, but basically there's a certain amount that can't be avoided. Experts believe, the McKinsey study was one of them on here, that you could improve this by about 15%. using the AMI data, being smart about balancing your feeders, finding the equipment issues. So that would be about a 1%, which translates into about $3.5 billion a year for the industry in the U.S. Another potential area of savings is through managing voltage more closely, also known as conservation voltage reduction, or CVR. The idea here is that utilities generally have to put in a margin of error in their voltage, pump it out of the substation slightly higher than it necessarily needs to be to stay within legal limits, between 126 and 114. So they, pump it out a little bit higher so it doesn't drop below that 114, because as you go out on the circuit, it gets lower. If you monitor it at the meter, which AMI does, then you can dial that down at the substation and actually reduce voltage by a few percentage points. And there have been a number of pilots finding reductions of 3 to 4% in energy consumption. And the way that works is through a lower voltage. Your lights are a tiny bit dimmer and things like that. So you actually reduce the consumption. So 3 to 4% is quite a large number. I mean, you're talking about something like 12 to 15 billion for the industry. All right. On the reliability, that's an interesting one, because, and one of my observations would be that electricity is probably the most efficient use of, or most attractive thing for us to purchase in terms of value for money. I mean, what we would be willing to pay to avoid an outage is a lot of money. We know how important electricity is in our lives. We use it. We depend on it more and more. We saw what happened after Sandy with people running around to Starbucks just trying to charge their iPhones. But it's very, very valuable to us, and we get an incredible bargain at the prices we pay in the sense of the value that we get from it. So when we look at the value of reliability, what we're trying to do here is to say, well, how much would people be willing to pay in order to have a stronger, more reliable grid that has fewer outages and shorter outages? There are a number of studies that have looked at this, and it's a little bit difficult to test. You do have real-world tests when real-world outages occur, but putting a value on that is difficult. So the way this is done is through surveys. So these surveys go out and talk to customers, different customer groups, talk about different types of interruptions. Does it occur in the middle of the afternoon, or does it occur in the middle of the night? Is it 5 minutes? Is it 4 hours? And then what's going on outside? Is it, in the middle of winter where it's very cold and you're relying on space heating, or is it, a nice spring day where you don't have as much going on from a usage perspective? So putting all of these things together, you get different values for different types of customers, as you would expect. An industrial customer who's having their plant shut down would be willing to pay quite a bit to avoid that from happening. And as you, of course, would predict, the shorter the outage, the less you would be willing to pay, and the more you would be willing to pay. You see the detailed results in that table. Then when you consolidate those for all the customers across the country and look at different times of year and add those up across the year and so on, based on the actual outages, and one of the metrics there is the average interruption duration across the country, and that in the U.S. is about 110 minutes a year per customer. So some customers are going to be much less. If you're in a place like New York City, it's going to be much, much less, and if you're off in a mountain cabin, it's going to be much higher. but the average is 110 minutes, which is pretty good to give an idea of what is possible. In Japan, that number is 10 minutes. So that doesn't mean that the U.S. should strive to get to that figure, but it does indicate that there's possible room for improvement. And then here you see the value associated with that, $80 billion a year, which is about 25% of what customers actually pay for their energy. So another way of saying that is customers are saying that they would be willing to pay 25% more on average to avoid all outages, which of course is not possible, but we can do better. Okay, so now I'm going to turn to Commonwealth Edison. And what they did is they went in and they made a proposal to their Public Utility Commission. They said, we want to roll out AMI. We see a number of benefits, benefits for customers, benefits for operations. And, you know, we want to put our money where our mouth is. So we are proposing that we set up some metrics with you and that we would actually pay financial penalties if we don't achieve those metrics, because we're highly confident that with AMI we will achieve those. So they proposed 9 metrics. And these, some of them are in distribution operations reliability and some in customer service. So the system average interruption frequency index is one of them. So that's the number of outages per year. And then the customer average interruption duration index. That's what I was talking about earlier about the 110 minutes being the average duration per customer per year. And then they also proposed a metric around controllable interruptions, which is where they're going out and performing service. On the customer service side, they believe they and plan to reduce the number of estimated bills, usage on inactive meters, and that's essentially somebody moves out, but somebody moves in and starts using energy without calling the utility, quite common. Unaccounted for energy, this is the energy theft, as another term for energy theft, and then uncollectible expense. So let me go through those in a little bit more detail. One element of this plan is that it's phased in, which is a great way to do this. So the metric, there's a metric for year 1, 2, 3, et cetera. AMI is being deployed over 10 years, and the utility expects to improve on these performance measures year over year, a little bit each time. So in this chart, you can see the FADI index and the predictions for how that'll improve over time. And this gives this gradual improvement gives time to really take in the data, process the data in the ways that Larsh was talking about it, and make changes in operations and deployment of distribution capital to achieve these kinds of things. On the penalty side, now these, again, were proposed by the utility. In essence, again, saying, you know, we're putting our money where our mouth is, we're going to deploy a couple $1 billion worth of AMI, and we essentially are guaranteeing that the customers are going to see the benefits. There's some penalties that they proposed, what they call a 5 basis point penalty, which is equal to a 0.05% reduction in the authorized return on equity. So say going from 11 to 10.95%. And that's for 8 of them. So the total could be as much as a 0.4% reduction, which is a lot of money. On the reliability side, I've put the 10-year targets that they've said they're going to achieve: a 20% improved safety, 15% KD. Then they have some regional things, and then they are going to improve the controllable interruptions by 75%. So they have quite an aggressive target there. And moving on to their other targets, you can see some very aggressive reductions in estimated bills and consumption on inactive meters. They find that because they set up their software to get an alarm when there's consumption on a meter that's supposed to be inactive. Reducing theft by 50%. Again, a very aggressive goal. You can see the other goals there. And then the penalties for customer service are also up to 5 BPS as well. I mentioned earlier about the phase-in of the performance targets. And one thing where it's great to work with regulators on is excluding extreme events. And their plan does exclude such events. And most utility reliability plans with their commissions do this. Nobody can foresee a Sandy coming in, and it's not fair to penalize the utility for not foreseeing Sandy. So these kinds of events are excluded from those metrics. But otherwise, the stuff, the operations and the equipment that the utility is in control over is subject to these performance targets. So using analytics to achieve the kind of goals that ComEd is talking about, the first principle here is what I call avoiding garbage in, garbage out. And the key point here is that AMI data is not perfect. We want to perform all these analytics to look at all these things we've been talking about. And we want to use that 15-minute data for everybody. In fact, my latest blog is on Smart Grid News, just published today, talking about all the possible uses of interval data. But before it can be effectively analyzed, it needs to be high quality. So there needs to be good IT system in place to take that raw data from the AMI system. And most of it, 98% of it, is great. But 2% can really affect the outcome of your analyses and needs to be put through validation and estimation of missing intervals. On the reliability side, analytics helps understand why the outages are occurring and then allows the targeting of investments. On the customer service side, again, identifying and diagnosing consumption in order to find those inactive meters that are using energy, and in particular the energy theft side. Another key area for customer service is targeting of energy efficiency and demand response programs. And this is basically finding those customers either who have very high usage compared to other similar customers, or in the case of demand response, have very high usage during peak periods in comparison with other customers. If you go out and target those customers, you can greatly improve the effectiveness of your demand response and energy efficiency spending. So with that, I think we're going to turn it back over to Aaron and answer some more questions.
Thanks, Chris. Before I get to the questions, I just wanted to make sure everybody knows that there's an opportunity to download our white paper here. And from there, you'll be able to see where you can get the slide deck that we're presenting today, too. A number of you have been asking how to get a hold of the material. So it'll be available from this website as well. Moving over to the questions section here, Chris, for you, how will AMI, this is an interesting question coming out of India, but I assume it'll apply to a number of different markets globally. Where do you think implementations of smart meters are going to help with distribution operations where utilities are actually government-run and losses are really high within the market?
I think the starting point of that is to understand where the losses are occurring. In this case, there are a lot of customers getting energy without paying for it. And there's some sort of general understanding of who those customers are, but more detailed understanding through some initial deployment of AMI. And, you don't have to go to 100% on day one, but you can deploy strategically, pick up the bigger customers, make sure that you're getting maybe all of the circuits, all of the substations that you're getting some data on, and start narrowing down where the losses are occurring. In the case of a developing country like India, there's a real policy question of how do you want to go after collecting those revenues, which is, on the one hand, the people using the energy are very poor, and so that's an important consideration. And for some of them anyway. So you may find, there's some areas where people who are better off or companies who are doing fine are ones that you want to go after aggressively to pay their bills. But the other side of that is the importance of collecting those revenues. So in India, we saw a huge outage, I believe it was last year, and quite lengthy, a day or so. And you have a situation there. I met with the Minister of Energy from India a few months back, and he was saying that, we've built all these power plants, but we're not collecting enough revenues to operate them all the time because you need money to buy fuel. So, it's very basic economics. The other thing is when you understand what's going on, you can also do things like prepayment or load limiting. So people who don't have money can get a basic limited amount of electricity and cover their basic needs, and deal with part of the problem that way.
Great. Here's a question for both of you. Do we think that cloud-based MDM is attractive for small, medium, and large utilities within the United States? When do we see that trend taking hold?
So let me start off with that one, and I think the answer to that is yes, and I think Chris can address some of the policy questions that might be limiting that adoption. But I think, if we look at what's going on today in smart metering, but smart grid even more generally, there's a lot of work to do this stuff. There's a lot of technology. There's a lot of sort of change management, transformation, and so forth. And I think, with the there's a number of utilities in different categories, and not necessarily small or large, but there's just some that say, look, I really want to have that leg up of having somebody with expertise help me get my systems in place and help me, through this transformation and maybe take over operations at some point in time. But to get started and to get the benefits going more quickly, I'm willing to work with this on a hosted basis or on a cloud-based solution.
Yeah, and on the policy side, again, that capturing the scale economies is great, and allowing the smaller utilities access to a lot of capability that it would be difficult to implement on their own, as well as the expertise side, not having to try to build up that expertise and taking advantage of a centralized solution. Some of the things you need there that you need to be careful about, of course, is data privacy and security. Utilities are rightly so very concerned about other companies, either other utilities or anybody else, getting access to their data. So such a service would have to have a very high level of security as one element, and another would be the very clear restrictions on access to data, so that if I'm utility A, when I access the system, I can see only my data and not anybody else's data. And it's a little bit more complicated because I may have 15 people that I want to be able to access the system. So the system's got to keep track of all those logins and the relationship between who can log in and what data they can see. An example, real-world example, is in Ontario, where the government, through the transmission system operator, the independent electric system operator, is providing a centralized MDM for all of the utilities there. There are between 70 and 80 utilities. Many of them have less than 10,000 customers, as an example, so they could never afford to implement this on their own. So they all have access to this and the capabilities of the system. And we're starting to see, in a couple of cases, we're starting to see some of the smaller utilities signing up for commercially available cloud-based systems. As these privacy and security issues are further addressed, I think we can expect to see more of them do that because of the fundamental economics. But so far, we only have some limited sort of security and privacy rules in place, and those standards are coming pretty quickly. So I would expect to see quite a bit more of that going forward.
And do you think this applies not just to North America? Do you see this as a trend that will extend to the rest of the world?
Very much so.
I think so.
Go ahead, Lars.
Yeah, I think the drivers and the functionalities that we're talking about are globally important, and I think we see different sort of principal targets for improvements and sort of priority use cases, if you will, for these kinds of investments. But I think the challenges of utilities globally are to be able to staff up and train to adopt these kinds of technologies and implement them. And I think that this is again where the opportunities of leveraging experience and shared knowledge and so forth is really important, and it can lead to this generally just about anywhere.
Specific example of that is Denmark, which has, as a country, has fewer electricity customers than New York City, but has about 160 utilities. So they are implementing similar to the Ontario model, and we're seeing many other countries look at something like this as well.
We're also seeing a lot of the telecom companies looking at this space and deciding that they'd like to have a role to play. And some of them, such as our alliance with Verizon, are offering that kind of service today. And I think we'll see more bundling of not just the MDM functions, but also some of the related communications and systems operations capabilities that can go along with that to create that value bundle for the utility.
So here's an interesting question. We talked about the benefits to the distribution and transmission folks as well as the consumer to some degree. Are there any benefits that AMI provides to the actual power plant and electricity generator?
I think you can look at the ability to provide a more reliable and a lower risk forecast for scheduling power plants, which goes to everything from operating conditions and maintenance windows to fuel procurements and so forth. So depending on what kind of utility you are and what kind of information is available from to the generator, if you're in unbundled or deregulated markets, things are a little different than if you're vertically integrated and own the generation. But I think in the end, this kind of information allows for a much more qualified and a much more up-to-date form of forecasting than I think we've been used to. And that, again, goes to both the operating metrics of a plant as well as the fuel and fuel costs, which form a big part of the margin of profitability on a power plant.
So, Aaron, when you mentioned generation, of course, Lars is talking about big central generation plants. Something else that jumped into my mind is renewable generation. And there are two sort of interesting applications here. One is on the solar side, and we really see this in Germany, in southern Germany, where there's actually enough solar installation in Bavaria to meet the annual peak demand. Now, of course, it can't serve all the energy because it's not on all the time. But what happens when you have that much solar is you get voltage problems in the system. So having the AMI data allows you to understand those better, and also when you bring those into a system and do something like a virtual power plant where you're turning distributed generation on and off, you can manage the effects on the system. Siemens is actually doing a pilot program in Munich along those lines. The other one is on wind power, and we know obviously you can't control that either. And we get a lot of excess wind. We see that in Texas, and what happens now is you turn it off. And they turn off the wind generators about 20% of the time in West Texas because the power isn't used by customers. So that comes back to demand response and pricing. So if you price that using the capability of AMI to support either time of use pricing or some sort of peak time pricing or even real-time pricing for the larger customers, then you get the customers who are using that energy when it's available. And, of course, the price goes down when you have too much wind, and they could use more and vice versa. The other piece of that is storage, and that's a key element supporting a lot of these things that we're talking about and where a lot of work is being done. In that case, I think we're still early in the game in terms of the availability of storage, but that's something else that's going to help us achieve all of these things we've been talking about.
Great. Well, I want to thank you, too. That was a really interesting discussion about using AMI and how we can better set goals for ourselves, how we can monitor the progress, and how we can report on it, and then some of the trends that we described during the Q&A session here. I think this was very, very useful. I did want to point out to everybody that we will be sending out the slides to everybody that has attended and registered, so those should be coming to you. And again, you can download the white paper at the link provided. And I want to thank Kristen Larsch for the presentation and wish everybody a good day here.